we had a few ideas at then, and me being me, I had a few opinions. I didn't need to share them all, but I did. But some of them didn't make sense at first, and unfortunately, they kind of drew an interesting crowd. So it turns out we need to tell people that you're not going to use GNU library, and that you're going to use a certain approach to things. At that point, it's like, you should replace System D as well. Yeah, and while I'm at it, I'm also going to eject Wayland, and I'm going to like put Xorg into the kernel, because that will solve the world's problems. Yeah, so there was a slight pivot, as they say. It all involves pointing fingers, really, when you really think about it. But yeah, it started off with a set of ideas that's come from being jaded from doing distro dev for way too many years. And that's kind of what it started out about. It's like, how do we fix the deployment of Linux distributions rather than just let's build another distro because fuck it, why not? They haven't
there's
seen
plenty of those.
Yeah, like Justin Bieber's had his share of the limelight, but there's others yet.
Well, there's
we can
the
have
Bieber
more
OS as
distros.
well.
Yeah, and there was like Hannah Montana Linux as well, wasn't there? Yeah, there was a few, but I'm sure we could slap Hyperland on a few of those now, couldn't we?
Surely.
Get some nice blur behind going. Oh yeah, who needs stars when you have blur?
Well, fun fact, I don't know if you know this one, but one of the first distros to ship Wayland was Rebecca Black OS.
Oh, I'm in the wrong industry. I can't go off anymore. Between me and my non-working microphone. Yeah, so I decided finally I was going to address all of the tooling issues, and I kind of looked at the way that I'd approached distros before, and I realised the approach and mentality was wrong. I was always trying to solve the deployed problem itself, where like I was always thinking, how is the user going to engage with this? That does matter, of course it does.
Sure.
Nobody wants to use something that's complete shit. But it was always entirely around the UX, and the tooling side always suffered, and it was always having to put out fires to fix even the most trivial of architectural issues. And one of the things that really, really irritated me is the lack of nice atomic updates in basically anything. And when I started looking around, like, say, well, OS Street was the primary example, because nothing else really existed a few years ago. Something really triggered me about having to reboot. And I get that if you're installing a kernel update, fair enough. You know, there's a new C or NSS libraries they've updated, fair enough. You know, like they're in memory, anything's residual, needs the entire reboot. Totally get that. If I'm installing a text editor and you want me to reboot, fuck off. Basically, that's my entire take on it. Like, I shouldn't have to. It just seems a chronic pain in the arse to do that. And I get it makes sense in more of an appliance point of view. Totally understand that. And there's a difference in context as well, because other projects they're interested in having an immutable, verifiable image. And for that, there ain't many options. So, makes sense. But as a desktop user, as somebody who's doing the development work, for me, it felt not just OS Street. There's other examples as well. They all have the same idea, you know, like it's an A/B swap up boot. That's all it is. Whether it's for partitions, volume groups, or as I'm sure somebody's going to tell me, Butterfly subvolumes, you know, with compression, and you know, like I can't stand Butterfly. I just can't.
If you want to talk about that, I'd definitely like to hear it at some point. You don't have to sidetrack right now. I can put it on the list. We can talk about it later if you want to.
Yeah, I don't know. I don't do the whole fad thing. I don't.
Fair.
I used EXT up until about 3 weeks ago. Like, and before that, I used the other file system that's dead. Anyway, one foot in the grave. Moving on. So, I thought I'd focus on a different problem from immutable. I thought the problem that matters to me is atomic.
Right.
And the reason that matters for me is because having done the whole distro engineering thing, there's so many things that are going to change over time. Mutating a live file system just is not a solution. I mean, we've all seen it, even with really good package managers. Once you start using pip against your user tree, forget about it.
Yeah.
It just don't matter anymore. Any package manager is break. Why is this file have a directory?
This is why a couple of years ago there was a PEP to basically force you to use a virtual environment by default. Like, if you're going to do Python, just do it in a virtual environment. Do not let it touch your system, like your core system.
Yeah. So, that's sort of the problem that I was coming from. Having to stat a file to know the status of the operating system kind of seemed a bit silly to the whole, and it's not me joining, the anti-Unix camp, but we've done this whole, that's the file system and everything is a file for so long that we've just accepted that the operating system is a database of files on disk, and we've left it at that. We've added more features to the file system to account for that, and I kind of felt a bit, file system's great, don't get me wrong, but I thought, surely we can go back to basics here and think about using actual databases and the right structures and using things like hard links. And so that's kind of where Moss came about. And if you're wondering where that name came from, it was the whole a Rolling Stone, blah, blah, because we could be rolling distro, and that has to become Boulder, Avalanche, Summit. That's where all of those names come from. We decided it's going to be rolling release, and it's going to be different to everyone, of course. So we set about doing an atomic implementation that would not require a reboot, and took a bit of experimentation. At first we used a symlink, and that every time that was decoded, that mangled all of the paths, and that kind of left us with a security issue. If you built something that resolved to one particular symlink and that was in that build configuration, you could abuse that to inject a path that didn't need to exist. I was like, fuck, that's not going to do. So we had a rethink on it. And then the current strategy for applying the file system, long story short, we create a hard link farm. It's the same as any other content addressable storage. You have a load of hashed files stuck in a directory somewhere, and then you just hard link them into place. The difference is, when we put that staging directory together, we're basically creating a new version of the user tree. Because we've enforced the user merge from the start, which meant we had an advantage. We didn't have to solve that problem. We know that everything is related to user. All of the symlinks in root, they go straight into user. So I thought, why don't we just swap user? That would seem to be the obvious thing to do, which we do now. So we use the rename at 2 syscall using the atomic exchange flag. It's over the website. Everyone looks at it and go, what the fuck is he even on about? Long story short, it is like everyone's looking at the website, but Serpent, I don't know, Adam and Eve. Nothing to do with Linux, apparently. But it will atomically exchange 2 directories in place. And that doesn't affect running processes. You will not get a busy error. You won't get bad file descriptors. The view that they saw of user at the time of execution is what they still see. So it means any new application launch will see the new user. You don't have to read, which is wonderful, fantastic. And that is, in a nutshell, how Moss works at the moment. There are certain downsides to that. Performance. Never did I think ext4 would have a performance issue with this, but it turns out, oh faithful, we were creating an extremely inappropriate number of hard links, to be quite honest with you. The maximum hard links for a file is 65k on ext4. Which, even if you think about it, does kind of sound a little bit low, if we're honest. You can have millions of hard links, but one file can only be hard linked up to 65,000 times.
Right.
Because somebody decided to use a 16-bit unsigned integer, not a larger number. When will we get the storage types right for times, dates, sizes, anything? Anyway.
Yeah, eventually. As we keep we identify problems and then we address them over time. And one day,
in 2039, maybe we'll do it then.
It's better than nothing.
So yeah, we discovered a bug a few weeks back where it was really irritating because the uniqueness of this was the weirdest part. So everything in our content addressable storage is based on the 128-bit XX hash. We chose it because it was just fast as all fuck and it seemed appropriate, and it was like Z standard, yeah, just whack them all in, multi-threading, yeah, 4 progress bars, fuck it, crack on. We stuck all the shiny in Rust as well, why not? You know, memory safety everywhere's. It downloads extra memory safeties off the internet for you and just sticks them in your extra memory safety disks. Because that's how it works, right?
Definitely.
Yeah. Oh yeah, of course. So we have like all these hashes, and it turns out when we're building the packages and we build these stone archives, which I'll get to the format in a minute, we didn't account for when a file would be empty.
Okay.
So it's quite happily accepting 0-byte files. That's fine. That's fine. It takes up no extra storage on disk.
Sure.
It takes up no extra storage in the archive itself. That's fine. But funnily enough, doesn't matter how many times you hash an empty file, it's going to have the same fucking hash. This is where the problem came out. Yes. Do you know all of those init.py and pyc files in Python, and you know all the config files that are part of the kernel? They're all empty files. So when you have a new transaction, and then you're recreating all of those files again, and then you've got thousands of empty files in one transaction, then you install another one. That's what we call an exponential fuck up. So within about 30 transactions, the system was like, no. We'd run out of file descriptors for hard links. So we created a workaround for it, which is basically like, if we see the known bad hash, then we'll just create a new empty file rather than hard link it, sorted. But that led us down this whole rabbit hole of, you would use MOS, you would install a package, and it would be excruciatingly slow, just for the first time. You'd run it again, it would be extremely freakishly quick. And nobody could figure it out, because the profile information was basically identical every single time. Except for sometimes, the ext4 call trace for find extents took ages, and sometimes it didn't. Turns out, even though you're using hard links and we're using all the relative APIs to do so, like link@, and make their at, it still has to go and find the hard links in the cache. And it primes that cache, it knows where they are, even though they're relatively linked. Anyway, that's just how it works, and I'm not going to insult it, but we do now default to FS. Because going from 30 seconds to 1.6 is a little bit better.
Definitely an improvement.
On an i9.
Yeah, that's a bit of an improvement.
Yeah. On an i9 with a terabyte NVMe SSD, it went from 30 seconds. So yeah, as I say, it's been a huge rabbit hole, but one of the next things we're looking at is actually using, instead of blitting millions of bajillions of bajillions of files, because we have a working Atomic app implementation, which is really, really nice, was like, well, we probably want a mutable now as well, but in a way that's actually useful to everyone without cutting off the developer experience, like having that nice compromise. So we kind of looked at what the Compose of S guys are doing over there, and then we realized with the way that MOS works at the moment, in it has databases for the entire system state. That's why sometimes we call it system state manager rather than package manager. So we have a database that's basically, if you imagine a stone file or an archive, it's split into several components. They're top level payloads. Each one has a fixed header, so we can just skip through the file really, really easily. But you have your metadata payload, which, as you can imagine, is just a bunch of keys with their types and their values. That's simple enough, like dependency, name, version, release, whatever. That stuff's boring. But then we have a layout payload, which defines how the file system is represented on disk when produced.
Oh. We lose him? Is that my side? Who disconnected there? I love Discord. What a great tool this is. Oh, wait, maybe it's my side? Oh, I'm at 5,000 milliseconds ping. Maybe that's my side, actually. Oh! Hello?
Hello?
I don't know. I was at 5,000 milliseconds ping. I don't know what happened there. That was... Yeah.
It was probably my verbal wall of text. It just slammed your network. Yeah, so the layout payload is representation of the file system, not the actual contained file system. Because that seemed to me to be the issue with pretty much most formats. They're basically a glorified tarball.
Right.
You can't diff a tarball realistically unless you're doing a binary diff, or, you know. So we have this layout payload which defines how they're going to be done. Then you have an index payload which is effectively a set of offsets keyed by the hash. And then we have the content payload, which at the moment is what we just unofficially we call a mega blob. It's every unique file whacked together and then compressed in one go with Z standard. So that's then reflected at a higher level within the database. So we have a system installation database which caches all of the metadata. We have the layout database as well. So you can imagine you have these various databases which all work together. So then when we emulate updating the system, because we have to create an entirely new state. So we're not upgrading the system. We don't know what the file system looked like anymore. We have to completely reproduce that view. So inside, it's not actually imperative. We had to pretend that it was. I know some people are drawing comparisons to certain other toolings, but it's not quite the same. But yeah, it's a pretendy imperative distro, if that makes sense. So we join a lot of queries together and we can produce this whole new file system in one go. And at the moment, as I said, we can do that now like in under a couple of seconds, like say 250,000 hard links. There's some code up there for creating a virtual file system in memory, which then optimizes the order. It uses the arena grid. So what it basically does is it rearranges where all of the files are going to go based on symlink resolution ahead of time to know what the conflicts will be. And then it writes them all in a file system optimized order using the relative APIs. It's pretty, but it basically translates to fast as fuck, which is what we want. So now we have all this working system and we have this deduplication stuff. We have these individual transactions. We decided take what we have now, and instead of writing out a new hard link tree, we could actually just write out I don't know the pronunciation, EROFS, the EROFS, the one that ComposeFS guys are looking at. So long story short, it's a read-only file system. That's all it's good for. You can only read with it, but it's optimized for read, and that's the key here. But it's been improved by the ComposeFS guys to work in conjunction with OverlayFS. Now, normally, I'm not a great fan of OverlayFS because it has some chronic performance issues when you have a separation between the bottom and upper layer, right? It's fucking hell on earth. However, we've come up with a slightly novel way of mingling our approach and their approach. Instead of writing out the hard link tree, we'll write out the metadata only EROFS file. We'll set all of the trusted redirects as the metadata back to the underlying storage in the overlay. So at the very bottom layer, you've got like my actual real disk. Yeah. And then all of the content store would still be in that disk there at this bottom layer. Then we'd have a pretend abstraction of the file system in EROFS. And through OverlayFS, it would represent a fake file system of the underlying view through that. But the thing is, instead of having to compute everything and it being really expensive, we already have this database there. So we can just spit out this file, and that tells OverlayFS to redirect everything to the lower layer, to the lower levels, and then you basically get the free immutable support. So instead of having to remount everything and everything like that, we're not going to do that. Instead, we're going to do something called a behind mount. You've probably heard of those lately.
No, I've not heard of that term actually.
They used to call them mount tucking or something like that was one of the names for it. It was a very informal idea, but the basic premise is instead of us having to remount and reboot the entire system, we're still going to use the EROFS stuff the way that the ComposeFS guys have been doing it, except for we don't have to compile it against the tree. We already have the data to generate it in place. So we can just spit out the EROFS file, no problem. Then with forgot what I was saying there. Confusion's not there. No, completely gone. Like the AeroFS, split it to disk. We bring up a new set of mounts in the mount stack. So say you've got like your existing user mount that was prepared in during the init RT. That's this existing overlay FS with the initially writable lower layer, but then the user tree and forced user merge make that all read-only immutable. But what we will do is create a new set of mounts, the same set of mounts, but for the new transaction behind that. So you've got this one set of mount, and you've got a higher set of mounts in the mount stack. So then when you pop it, the new one is here, that one's gone, and you haven't violated the root namespaces all the way through the tree. So you still get that live swap. You still get the very, very fast blitz. You still get atomics. You still get immutable, all mixed up in one package. So that's the next steps of it, which is going to be kind of cool to be honest with you. So a modular, immutable atomic.
I'm trying to keep up with what you're saying here. But, you know, I feel like SerpentOS would do a really good job with having like a 2-hour essay video just explaining how this system works. Because I think the short description you have there, I can understand why people are kind of confused, because it sounds, because atomic has now become kind of the term for things like silver blue and things like that as well. A lot of people are kind of confused, like, how is this different from an OS tree distro? Like, isn't this just the exact same thing? Yeah.